Hello, pre-calculus class. Today's lesson is about vectors in space. We're really just going to get comfortable with plotting in 3 dimensions and then start talking about vectors and doing a few calculations with them. There'll be 2 more lessons in this section, all on vectors in space. This is chapter 9, section 6 of your textbook. Go ahead, read over this warm-up, pause it, and then when you unpause it, you will see the answers. Okay, here's your answers. The x-intercept, you just plug in y of 0. So I did that right here and solve for x and get -3. The y-intercept, you plug in an x of 0. So when you plug in an x of 0, you end up with y is 6, or you just know the y-intercept is 6. To graph this equation, since it's in standard form, I quickly found the zeros. I can cover up this one and divide by -2 to get the y-intercept, cover up this one, divide by -3 to get the x-intercept, and I can plot those. Or I can solve it for y and get it in slope-intercept form, plot the intercept at -3.5, which we already knew, and then walk the slope. Since it's negative, I know the line's coming down. So instead of going down 3, right 2, I actually went up 3, left 2. So regardless of how you plot it, it should look like that. Okay, so I know you guys are good at plotting in 2 dimensions. Now what we have is space, so not just a plane, not just a coordinate plane, but space. So we have a 3-dimensional coordinate system. We have x, which you can see is forward and back. We have y, which is right and left. And we have z, which is our new coordinate, which is up is positive, and down. So we have ordered triples, or triplets, and you can see the point 3, 5, 4 goes 3 forward, and then 5 to the right, because that's your y, and then up 4. And there's the point in space. What's hard is you're plotting 3 dimensions on a 2-dimensional piece of paper, and so unless you kind of show the trajectory to get there, it's hard to know, or at least you have the ordered pair. And you're going to see we'll have a little problem with that later. And this is really helpful, so you should pause it and take down a few notes before the next slide. The other thing that's different is we're used to x, y being right and left. X being right and left and y being up, down. Now x is front, back, and y is right, left. All right, so this slide is just more helpful. Some people can hold up their hand to think about the plotting in space, and they use their thumb as the z, their wrist as the y, and their pointer finger as the x. Note here we're going to do problems like this one, where you can plot a rectangular prism by being given 2 corners. So this is the rectangular prism defined by the point 0, 0, 0 and the point 2, 3, 4. And I'll show you how to do that in another slide. Note there's 3 planes. We have the XY plane, and that means z is 0, and that's kind of just this flat surface here in pink. We have the YZ plane, which is in blue, and that was when x is 0. And we have the XZ plane, which is y is 0. So if you're plotting in 3 dimensions, but one of the dimensions is 0, it's like you're plotting in 2 dimensions. And then likewise, you can have equations that get plotted. So if I'm plotting in 3 dimensions and I say plot the equation y equals 4, you go to y is 4, and then the x can be anything and the z can be anything. So it's an entire plane y equals 4. Here's the plane z equals 3. And if I was interested in the plane x equals 1, let me get a pen here. If I was to plot the plane x equals 1, I'd go to x is 1, and then z could be anything, so it goes up and down, and y could be anything, so it goes right and left. So it's this plane. Oh, I kind of made it a mess, but this would be your x equals 1 plane. All right, go ahead and try to plot these 3 points. Note this is some triangular graph paper, and I know it's going to be hard at home because you don't have this graph paper, but I will give you a page in the blank notes file that's just graph paper, and if you have the ability to print it out, you could. You might be able to just search in Google for three-dimensional plotting paper or triangular plotting paper and try it that way, just online. But note, here's your x-axis, and it's going, this is positive, and then here's your negative x. Here's your y-axis. That's positive, and here's negative. And here's your z, positive. Up is positive, and down is negative. All right, go ahead and pause it here. Try to plot them on your own, and then you can see how to do it. Okay, so first thing I'm going to plot is point A. So I go 1 for x, and then 3 for y, and then up 4. And I just do it in that order. So this is point A. B is going to be 2 for x, so right there. 0 for y, so, right, left, nothing. And then up 3. So there is point C. Oh, I'm sorry, that was B. And lastly, we have C. No x, 4 to the right, and then down 1. So this is point C. How'd you do? All right, so this is a three-dimensional equation, and we can plot it. We can do it by finding the intercepts and then sketching the plane. So to find the intercepts, what you want to do is you want to plug in 0 for x and 0 for y and solve for z. You want to plug in 0 for x and 0 for z and solve for y. And you want to plug in 0 for y and 0 for z and solve for x. Once you do that, we can plot those points and connect them to form a plane. Go ahead and pause it and find those 3 points. All right, here are your points. The first point is 0, 0, 6. The next point is 0, 10, 0. And the last one is 2.5, 0, 0. So if we plot these, I'm going to plot the x one first. That's x, that's y, and that's z. So I'm going to go 2.5 forward, and that's your x-intercept. Your y-intercept is 10 over, so 2, 4, 6, 8, 10. And your z-intercept is 6, 2, 4, 6. So those are the 3 intercepts, and just like we plotted the equation of a line, we found the intercepts and connected them. We can do the same thing here. So if we connect this, and connect this, and we connect this, you can see it's cut off by the 3 planes, but it really does continue forever in these 3 directions, if you will. So now we have a plane formed by these 3 lines. I can kind of just show that plane here, kind of cutting off the corner. All right, so you might see a problem or two like this in the homework tonight. Okay, this is a problem where you're trying to plot a 3-dimensional rectangular prism on this 2-dimensional plane surface. You're given these 2 opposite vertices, and what you want to do first is to plot those. Go ahead and pause it. Okay, so those are the 2 points. Hopefully you plotted them well. I kind of color-coded them for you. Now you can see over here to the right, I kind of wrote down spaces for 6 more ordered triples. So in a rectangular prism, you have 8 vertices. There's 4 points on top, forming the top of the box, and 4 points on the bottom, forming the bottom of the box. Some people are really good at visualizing the fact that these are opposite corners of a rectangular prism. but it can be tricky. So what I do is find the combinations of all vertices, and that's going, or all coordinates, and that's going to give us our 8 vertices. So on this first column with the first point, they're all going to be 2s because it's really a combination problem, and these are all going to be 5s. And then here you got to make sure you've got 2, -1, and we have a 5 here, so the other one's got to be a 2. And then we're going to pull up the 4, and one will be with a 5, and one will be with a 2. And that's all combinations with a 2 in the X position. For the 5 in the X position, you're going to have a 4 and the 5, and then you're going to have the -1, one with a 2 for Z, and one with a 5 for Z. Now that you have those, go ahead and plot them. You can pause it here. All right, so the first 4 I plotted in blue, and you will see that it'll end up being the back of our box. Pause it again. Now you can see I plotted these points here, and we got the front of our box. Now it's easy to just finish the rectangular prism. We can connect these 2, and these 2, and these 2, and these 2. So you can see that this was one of our original points, and this was one of our original points, and that they're the opposite vertices of a rectangular prism. You will be asked to do this for homework as well, so you might need to refer back to this if you get stuck. All right, for those of you that aren't as visual or have an easy time with the spatial plotting, you're going to like this better. So this says if we have 2 points in space, so you can see an ordered triple and another ordered triple, we can quickly find the distance between these 2 points in space by this formula. It looks just like our distance formula in the coordinate plane, but it adds our Z component. Pretty straightforward. So let's do that with the first example, and then you'll try the second one on your own. All right, so we'll do D equals the square root. And we just have to find a bunch of differences. It really doesn't matter, since we'll be squaring it, whether you take P2 minus P1 or P1 minus P2. So I'm just going to do P1 minus P2. So -2 minus 4 is -6 squared, plus 4 minus -1 is 5 squared, plus 0 minus -5 is 5 squared. And you end up with the square root of 36 plus 25 plus 25, which is the square root of 86. And of course, what's that? A little bit more than 9. Okay, go ahead and pause it here and try to do the second one on your own. And here's your answer. The square root of 66, or approximately 8.1. Please note, this represents the distance between 2 points in space. We will be calculating the magnitude of a vector in space in a future lesson, which really just takes this formula and makes one of the ordered triples be the point 0, 0, 0. And thus you end up with your magnitude equals the square root of x squared plus y squared plus z squared. Remember, magnitude is the length of a vector. So that is to come. Okay, now we're on the last slide of the video, and we're going to start talking about position vectors in space. Note, in 2 dimensions, we just had your I and j component. Now we're adding in your k component, 3 dimensions. So I is the unit vector in the direction of the positive x-axis, j is the unit vector in the direction of the positive y-axis, and k is the unit vector in the direction of the positive z-axis. A vector can also be written as a comma b comma c. So if we're given 2 points in space and we want to find the position vector between them, note that direction matters. So I'll just write this a little bigger. A vector v is P1 to P2. So what we need to do is for each component of P2 and P1, subtract P1 from P2. So I'll do it here. Here we have 2 points, and we want to write the vector P1 to P2. So the vector will be 4 minus -2, which is 6, -1 minus 4, which is -5, and -5 minus 0, which is -5. We could also write it as 6i minus 5j minus 5k. You go ahead and pause it here and do the next problem, and when you unpause it, you will see the answer. All right, so the vector for the second problem is -5i plus 4j minus 5k. All right, that's the last problem in the lesson. Go ahead and try your homework assignment.